Hello, everyone. The next speaker is Professor Hao Wu from Tsinghua University. The title of her talk is Connection Probabilities for Loop NO Models and BPZ Equations. Welcome, Professor Wu.
It's very nice to see you. Today I'm going to talk about connection probabilities for loop OM model and the BPZ equation. So the loop OM model is a very classical model in probability, and BPZ equation is a very standard equation in CFT. So we're going to see some connection between probability and the conformal field theory. Okay, so my talk will have 5 parts. First is a brief background on loop OM model, and then I will introduce Meander matrix, Coulomb gas integral, and the pure partition function. And finally, I will focus on one specific example on uniform spanning tree. Okay, so let us first look at what is the definition of the loop OM model. To make everything simple, I just focus on the honeycomb lattice. So this is a honeycomb lattice, and we're going to consider bound percolation model on this honeycomb lattice. So a loop configuration means that we ask some of the edge to be open and some of the edge to be closed, but we only allow loop configurations inside my configuration. So everything have to all the open edges have to form into a loop. So this is a typical loop configuration in this honeycomb lattice. And for the probability measure, what I do is that first I count how many open edges are there in this configuration. And then I count how many loops are there in this configuration. And then the probability measure is proportional to P to the number of the open edges times N to the number of the loops. So here P we call the edge weight. N is what we call the loop weight. So this is a definition of loop model. So it is very simple. And this model has a very long history in physics. So there are various conjectures about this model, and today I'm going to focus on this one particular conjecture. So this conjecture says that, of course, the limiting behavior or large-scale behavior of this loop OM model going to depend on the parameter P and N. So there is a conjecture says that if I fix my N, the loop weight parameter N, between 0 and 2, and then there going to exist a very special value on P, which we call PCN here. So the formula is given by 1 over square root of 2 plus square root of 2 minus n. So there's a very specific PC, and the conjecture says that if P is less than PC, then this model is subcritical. By subcritical, we mean that the point-point correlation function is going to decay exponentially fast. And when P equals PC, this model is believed to be critical. By critical, I mean that the point-point correlation function will decay at a polynomial rate. And here, this more interesting phenomenon for this model is that there is a third phase when P bigger than PC. So if you are familiar with like a Bernoulli standard Bernoulli bound percolation, we're going to say that when P is bigger than PC, this is supercritical. However, in this loop OM model, when P is bigger than PC, this model is still critical. So there are two critical phases. One is the critical phase, P equals PC. We call this as the dense critical phase. Another critical phase is P bigger than PC. And we call this, the previous one is the dilute dense critical phase, and this one is the dense critical phase. Here is a diagram between the N and the P. So the horizontal line is N, the vertical line is P, and this blue curve is this critical line. So then the conjecture says that if you're on the critical line, the model is critical, and if above this green curve, the model is still critical, but in a different critical phase. Okay, so this is the famous conjecture for the loop OM model by Nienhaus. And for this conjecture, in fact, there are 4 models that already prove that this conjecture is true. So the first one is called when n equals 0 and p equals 1. This is what we say the uniform spanning tree model. So this model is indeed conformally invariant in the scaling limit. It was proved by Lawler, Schramm, and Werner around 2000. The next one is n equals 1, p equals 1. So this is the standard Bernoulli bound percolation. So this is also known to be conformally invariant in the scaling limit. The third one is called FK-Ising model. So this is p equals 1, n equals the square root of 2. So this is also proved to be conformally invariant. The last one is n equals 1, p equals 1 over square root of 3. So this is the the most famous Ising model on the two-dimensional lattice. So for these two models, they are also proved to be conformally invariant by the group of Smirnov. Okay, so this is the full model that we already know that they are conformally invariant. So today I'm going to talk about connection probability for this model. So what do I mean by connection probability? So I consider this loop model in a polygon. So this is a polygon with a 6 marked point, x1 to x6. For this model, I require the alternating boundary condition. This means that all the edges from 1 to 2 are believed to be open, and all the edges between 3 and 4 are open. All the edges between 5 and 6 are open. So this is my boundary data. Then for the inside of the edges, for the edges inside the domain, I just sample them according to the probability measure. So for instance, this is a 5 possibility for the 5 possible configuration in this loop model. So now what is the connection probability? So the connection probability means that because we only consider loop configuration, we know that there are going to be loop among these 6 marked boundary points. And according to this loop, this 6 marked points are going to be connected pairwise by disjoint curves. And for 6 points on the boundary, we know that there are going to be 5 possibilities for the connectivity. For instance, 1 is connected to 2 here, and 3 is connected to 4, 5 is connected to 6. But in this picture, 1 is connected to 6, 2 is connected to 3, and 4 is connected to 5. So they are total, when there are 6 boundary on the 6 marked point on the boundary, there are going to be 5 possible pairwise connective link pattern in this configuration. And my question is, what is the probability for each of these 5 pictures to appear in my configuration? And the conjecture says that, so if we fix the parameter n between 0 and 2, and we fix a kappa related to n in this way, so it is between 8 and 8, then we are able to calculate what is the probability for each of the 5 pictures to appear in my configuration. So the probability is given by this formula here. So beta means my boundary condition. Alpha means the interior connectivity pattern. So this probability, if the size of the lattice goes to 0, it converges to something to the right-hand side. In this right-hand side, there are 3 quantities. The first one is what we call mean matrix. The denominator F beta is what we call Coulomb gas integral. And the Z alpha is what we call pure partition functions. So now I'm gonna introduce these 3 quantities one by one, and then go back to this conjecture again. So here I also need to mention that if the polygon is very simple, for instance, if the polygon is just a rectangle, so there are only 4 marked points on the boundary, then for the Bernoulli bound percolation, this is exactly the famous Cartesius formula. And for FK-Ising model, this is also known. So basically, this conjecture is a more general polygon conjecture for Cartesius formula. Okay, so now let us see what are these 3 quantities. First, mean matrix. So the mean matrix is the matrix. The size of the matrix is a Catalan number times Catalan number. So it's a very big matrix. At each entry, we encode the entry by this link pattern alpha and beta. So if I draw alpha in this way, beta in this way, and then I take horizontal reflection of beta with respect to the real line and put it on bottom of alpha. So this is what we call the meander between alpha and beta. And then we calculate how many loops are there in this meander. Then for this matrix at the entry alpha and beta, the number is given by n to the number of the loops in the meander. So this is the definition of the meander matrix. This meander matrix is very well understood in representation theory. And the most relevant conclusion to my talk is that we want to understand when does this matrix is invertible. So this is also known. So if we fix n between -2 and 2, the meander matrix is invertible if and only if kappa is between 0 and 8 and remove some rational number. So this is already very well understood, and this is also this is the most important conclusion for this meander matrix related to my talk. So here I also want to mention that all the models we are interested are those rational numbers, so they are removed from this set, which means that for all the models we are interested, all the meander matrix are not invertible there. Okay, so this is the first quantity. Second, Coulomb gas integral. So this name is from a conformal field theory. So for Coulomb gas integral, in fact, it is a very explicit formula. It's a big integral. The integral is defined in this way. So first, we encode the boundary data by this link pattern A1, B1, A2, B2 to AN, BN. So this is a pair link pattern. And then we define our integral in this way. So first, this is the integration surface. So U1 is integrated from A1 to B1. UN is integrated from XAN to BN. So this is our integration surface. And the integrand is basically a polynomial. So this is also very explicit. So X are the points on the boundary. So this is the boundary data. U are the integral variables. Okay, so this is a very concrete integral formula. Here, I also need to mention that this integrand function is a multi-valued, complex-valued function. So in order to fix our definition, we need to fix which branch we are chosen. And remember that our ultimate goal is to prove the conjecture that this Coulomb gas integral will give us some probability. So therefore, in fact, when we choose the branch of this integrand function, we hope that in the end, after the integration, this function is going to be positive because it's going to appear in my probability formula. So therefore, the branch we choose for this multi-valued integrand is chosen to be real and positive in the largest possible set. So this is the largest possible set to make it to be real and positive. And the integration surface is the integration surface among the it's among the Programmer contour around the 2 points. So for this contour, we see that the contour surrounds each marked point clockwise once and counterclockwise once. So this is a well-defined integration surface. So this is a very concrete formula. So now why we are interested in this complicated integral. So why it appears in the star is that this is also the prediction from the physicists that they use the representation theory of Virasoro algebra to generate this system of the solution in this way. And they realize that if you write down your integral formula in this way, they are always the solution to this second order BPZ equations. So this is their original motivation. So they realize that this BPZ equation is very important in conformal field theory, and they try to generate some solution to such equation. And they realize that if you write down the integral formula in this way, you're gonna have this one we're gonna be solution to the BPZ equation. And if I already tell you the answer, in fact, it is very easy to check that they are indeed the solution. You just naively switch the differential operator with the integration formula, with the integration, and you check that this polynomial already vanish after you operate on this differential operator. And then you need to choose this integration surface carefully to guarantee that this is a legal operation. Okay, so this is the Coulomb gas integral. And the reason we are interested is that they are solutions to the BPZ equation. Okay, so now we know that this is a family of solution to the BPZ equation. And now what's the property of those integrals? Now we want to understand the properties of these integrals. So first, in fact, we want to understand whether they are always positive, because we really want to understand eventually it's going to appear in my probability formula. So at least I need them to be positive in order to be qualified to appear in my probability formula. And the conclusion is that when kappa between A0 and 8, those integrals, they are indeed positive. And when kappa equals A0 and 8, in fact, they vanish. And we even know how what is the rate when it goes to 0. So when kappa goes to A0, if we normalize by kappa minus A0, it's going to be some positive limit. When kappa goes to 8, if we normalize kappa minus 8 to the power n, it will also be a positive limit. So at these two terminal values, they vanish, and we even know how to normalize them in order to get positive limits. And then when kappa is less than A0, in fact, these integrals are going to fluctuate. So they can both positive and negative. Okay, so this is the property of the Coulomb gas integral. And next, we're going to introduce pure partition functions. So pure partition functions, by definition, they are also solution to this BPZ equation, but this is a different collection of the solution to the BPZ equation. So in the previous Coulomb gas integral, so this is an integral, and we know that they are solution to the BPZ equation. For this pure partition function, they are also solution to the BPZ equation, but they are not defined in that an explicit way. In fact, we define them by setting a particular boundary data here. So we set the boundary data to be in this way. So when 2 points are very close to each other, we require this solution to explode at a certain rate. And we normalize this explosion. And after the normalization, we require that it is going to converge to some limit. And the reason for choose this particular boundary data is that because of our ultimate goal is to prove that it's going to appear in my probability formula. When we want to calculate the probability, in fact, we realize that the probability will have certain compatibility. This means that suppose we want to calculate the probability of the three curves behave in this way. And if the 2 points are very close to each other, xj and xj plus 1 are very close to each other, we of course believe that the three curve probability will converge to the 2 curve case. So if the 2 points are very close to each other. So if we really want to understand the limit of the probability, this collection of the limit will have compatibility in this way. So if the 2 points are very close to each other, then the probability for n curve should be consistent with the probability with n-1 curve. So this is the compatibility we desire if we really want to understand the probability. And this boundary data is chosen exactly in the way that to make the probability conjecture to be compatible in this way. Okay, so now here we see that we have a system BPZ equation. We fix a certain boundary data, but now it is not clear that they're going to exist the solution with your particular chosen boundary data, because this boundary data is very tough. So it is not the usual boundary data we see in the PDE theorem. So in fact, it is requires that it's when the point is approaching the definition domain boundary, it have to explode at a certain rate. And after you normalize by this explosion, it have to converge to something you already well defined. So this is a very tough boundary data. In fact, after we impose on this boundary data, it is not clear whether you still have solution to the BPZ sequence, to the BPZ equation that really satisfy your boundary data. So in fact, the first non-trivial conclusion is that once you set up this boundary data, the collection of pure functions exists and is unique up to a global multiplicative constant. So they exist and they are unique. And for the existence and the uniqueness, in fact, there's a very long history. For the uniqueness, it was proved by Floch and Coulomb around 2010, and it was published in 2015. And for the existence, there are at least 5 papers addressing the existence of such solutions. So for instance, the first one is to construct the solution of this pure partition function using Coulomb gas integral. But there, the caveat is that they have to always remove rational functions. However, all the models we are interested are all rational numbers. And the second and the third works related to me. So there we construct the solutions for kappa between 0 and 4 and the kappa between 0 and 6 and using different tools. But there we don't need to remove the rational numbers. And the last two is about the fourth one is by the group of Xin-Sun that they construct the solution using LQG welding technique. Okay, so but overall, now we already know that when kappa between 0 and 8, all the pure partition function, they exist and they are unique up to a multiplicative constant. Okay, so this is the pure partition function. Now, some properties of this pure partition function. So the properties is that, in fact, this pure partition function, they are linearly independent and they form a basis for the solution space. And they are always positive. So this is good for us because we want them to be probability. So they have to be at least positive. Okay, so they are always positive. And when kappa goes to 8, we know that they're going to vanish. And we even know what is the rate when they goes to 0. So the vanishing rate is 8 minus kappa to the power n minus 1. When then kappa goes to 0, In fact, we also know that it's going to vanish, but it vanishes at an exponential rate. So in fact, if when kappa goes to 0, we know that this Z alpha will decay like exponentially fast in kappa. So this is not my work. This is work of Evelina Peltola and Yilin Wang, that both of them are my co-authors and also good friends. So they investigate when kappa goes to 0, in fact, this pure partition function also gonna vanish. And here, in fact, this part is related to the large deviation principle of the SLE process. Okay, so this is the property for pure partition functions. Now we see that Coulomb-Gas integral is introduced as a very explicit integral, and they are solution to this BPZ equation. Pure partition function, they are also solution to this BPZ equation. So now let us discuss what's the relation between these two collections of solutions. So here we already say that this pure partition function, they are linearly independent and form a basis for the solution space. Coulomb-Gas is also a solution. So therefore, the Coulomb-Gas can be written as a linear combination of the pure partition functions. And indeed, this is case. And the linear combination coefficient is given exactly by this Meander matrix. So this is how these three quantities are related to each other. So pure partition function and the Coulomb-Gas, both of them are solution to the BPZ equation, but there's two different collection of the solutions. Pure partition function, they form a basis, so they are linearly independent. And the Coulomb-Gas can be written as a linear combination of pure partition function. And this linear combination coefficient is given exactly by this Meander matrix. So here we also want to mention that by this formula, we can already see that Coulomb-Gas integral, they are not always linearly independent. Because if you want to understand whether they are linearly independent or not, it is equivalent to understand whether this matrix is invertible or not. And for this matrix, we already know that they are not always invertible. In particular, at particular rational numbers, this matrix is not invertible. And all the models we are interested are in this family. So in this family, so all the models we are interested for the Coulomb-Gas integral, they are not linearly independent. So they can't generate the whole space of the solution space. Okay, so this is the relation between these three quantities. Now we can go back to this conjecture. So the conjecture asks if you are in a loop or model in a polygon, you want to calculate this probability. And this probability is given by this right-hand side. So Meander matrix times pure partition function divided by the Coulomb-Gas integral. So now we can already see that because this Coulomb-Gas integral is a linear, can be written as the linear combination of the pure partition function. So here we can already check that if you summing over all possible alpha in the right-hand side, it does sum up to 1. So this makes sense because this is the probability, and if you're summing up all possible alphas, it should sum up to 1. So, and this is summing up to 1 relation is exactly the relation we see on this previous page. Okay, so this is the conjecture for the loop or model. And for this conjecture, we already know that there are 4 models that are proved to be conformally invariant in this loop model. And for all these 4 models, we can also prove this probability, this conjecture formula is true. So for uniform spanning tree, this is correct. For percolation, this is correct. For FK-Ising, this is correct. And for Ising, this is also known. So this is in a series of papers with my co-author and my students. So here I also want to mention that there are very specific value in this 3 model. So one is percolation. For percolation, it corresponds to kappa equals 6. And in this case, in fact, we know that this Coulomb-Gas integral, although it is very complicated, but we know that they all simplify to 1. So they don't depend on boundary data, and they don't depend on the x location of the x. And this is exactly consistent with what we believe on the what we know already from the percolation, that for percolation model, boundary data has nothing to do with the model. So the boundary data doesn't influence the model. And another value is very special here is for Ising model. For Ising model, kappa equals 3, and this Coulomb-Gas can be written in a very explicit way. So it is a Pfaffian between of this matrix. And here we also see that this Pfaffian, so the right-hand side has nothing to do with beta, so it is independent of the boundary data as well. So here, why these two cases are very specific here. So the Coulomb gas is very complicated, and in general, they depend on the boundary data. But for this two particular model, they doesn't depend on the boundary data. So in fact, this is related to a very famous conjecture between Ising model here and the percolation. So there is a very famous conjecture says that if you consider the Ising model on the hexagonal lattice, if the temperature is at T equals Tc, the critical temperature, so it is believed to related to SLE3. But if the temperature is above critical, so the temperature T is above Tc, then everything going to converge to the same limit as the percolation. So percolation is related to Ising in this way. So one is the critical temperature scaling limit. Another one is the supercritical, so T or the T bigger than Tc scaling limit. So they are related in this way. And here it also connects to, this is also related to the connection that these two partition functions, they are very specific. So so the boundary data doesn't appear in this Coulomb gas integral. Okay, so this is the conjecture. And now I'm going to focus one very particular model here. So the first one is uniform spanning tree. Uniform spanning tree. Okay, so for uniform spanning tree, I write down this explicit formula here. So in fact, this is basically repeat the formula on the previous page. But the formula on the previous page, we know that this formula here, when kappa goes to 8, all the three quantity goes to 0. So the meander matrix goes to 0, pure partition function goes to 0, and the Coulomb gas goes to 0. But we already understand how they normalize in order to get a positive limit. So in fact, we know that for the uniform spanning tree, when kappa goes to 8, the right-hand side is still has a positive limit. And here the formula will become, so first we need to correctly normalize the meander matrix. So this is called the renormalized meander matrix. And then for the pure partition function, we also need to normalize it properly so that there is a positive limit. And for the Coulomb gas integral, we also need to normalize it properly so that there is a positive limit. So after the correct normalization, all the three quantities will become positive. And now all these three quantities will become the renormalized version of the quantity. So the renormalized meander matrix, renormalized Coulomb gas integral, renormalize the pure partition functions. Here, there's a very important property here is that this renormalized meander matrix, it is invertible. Okay, so this is the formula for the uniform spanning tree. And why this formula? In fact, for this formula, so we are not the first one to look at such probability. In fact, there are previous work to understand the probability, such connection probability in uniform spanning tree by Dubeta, Kenyon, and Wilson. And in fact, even in the second paper by Kenyon and Wilson, they also predict what is the limit, what is the probability to the left-hand side. So there is a probability for the left-hand side in their paper, but in fact, it is very far from very far to understand why their limit is the same as our limit on the right-hand side. In fact, we don't prove that their limit is the same as our answer to the right-hand side directly. So we prove that both of them are the probability, so therefore they're the same. In fact, we don't know how to justify that their answer is the same as our answers directly. Okay, so this is the conclusion for uniform spanning tree. And so this page is about how we prove this kind of formula. So the proof basically has 3 steps. First, we need to identify the limit of allomorphic observable. So here, this is the usual common step in all these 4 models that we try to prove conformal invariance. So basically, the first step is to construct some discrete observables and show that we understand that is limit in the scaling limit. And the second step, once we know what is this observable is, then we can derive the Liouville driving function of the curve. And the last step is that we use the refined analysis of the martingale given by the ratio between pure partition function and the Coulomb gas, and then use optional stopping theorem to prove the conclusion. So this is the basic strategy when we prove all these 4 formulas. But in fact, in all these steps, the first step is the most important one, and it is the most difficult one. In fact, usually for the first step, the proof is very short. It's usually 2 or 3 pages. But in fact, it took the longest time to understand what is the proper observable behind the model. And once we know the first step, from the first to the second and from the second to the third, they're basically technical proofs. So they are very long, but we know that we're gonna finish them in a finite time as long as we understand the first step. Okay, so this is the proof strategy for this kind of formula. And now I want to mention one interesting property for this uniform spanning tree. So why it is special? So it is special in the sense that for uniform spanning tree, in fact, in physics, conformal field theory, the physicists believe that this model is related to logarithmic conformal field theory. So not the usual, like for Ising model, it is believed to be related to the minimal model, and the conformal field theory is the usual conformal field theory. But for uniform spanning tree, physicists believe that it's going to relate it to logarithmic CFT. And what do we mean by logarithmic CFT? In fact, it is not so clear as far as I understand. But one way to understand this logarithmic correction is that they can take the OPE expansion of the conformal field theory and to see some logarithmic correction in this OPE expansion. So this formula is copied from a paper by Gurari in 1993. So this is the year that before SLE techniques was known. So there they already predict that uniform spanning tree is related to the logarithmic conformal field theory, and they even predict what is the OPE expansion for this anticipated field 1512. So this is what we believe in physics. And now for this OPE, for this uniform spanning tree, now in fact we can understand more in a more mathematical way, where do we see this logarithmic correction? And the concrete answer to this question is that we consider the associated Coulomb gas integral here, and we take the OPE expansion or Frobenius series extension or Taylor expansion of this Coulomb gas integral, and then we realize that the leading order is a polynomial of to the power 1/4. But for the leading order, we're gonna see a logarithmic correction there. So this is not observed before. Like if for kappa less than 8, we can also do the same OPE expansion for the Coulomb gas integral. But the leading order is always polynomial. But when kappa equals 8, we can already see that we have a logarithmic correction in this leading order. So this logarithmic correction, if we believe that the uniform spanning tree is related to the logarithmic conformal field theory, we can match it with what we believe in the OPE expansion of the correlation function in logarithmic CFT. Here, in fact, we provide a first mathematic proof that the uniform spanning tree should relate to the logarithmic CFT. So there is logarithmic correction in the OPE expansion on the correlation function. Okay, so this is the special property for the uniform spanning tree, and here is the references that related to me to this talk. Okay, thanks for your attention.